Yes, so my name is Marcus Elvert. I'm a research scientist, senior scientist at Marum, University of Bremen, Germany. I'm also responsible for the labs here, organic geochemistry-wise, including a lot of mass spectrometers, isotope ratio mass spectrometers, liquid chromatograph mass spectrometers, and so forth. So it's a technical challenge and also scientifically of interest, especially regarding greenhouse gases.
Yeah. So what kind of research are you doing with all these machines?
We specifically are focusing on organic molecules that could be related to biogeochemical processes, either metabolites, so greenhouse gases, either produced or consumed within the marine environment, so in the water column or the sediments. And what we also are focusing on are the remnants of this turnover by looking at the cell membrane components, which are lipid biomarkers, and these have a molecular structure that could actually be preserved in the sediment, in the sedimentary record for up to 1 billion years. So it's like a dinosaur bone, I always explain to the people. It's just a molecule, but we can trace it or those ones with the machines.
Wow. And so that gives you then information about climate from many years ago?
Yes, it does. So specifically, we firstly see from which kind of organisms it comes from. So
Yeah.
in many cases, that's already informative, giving us information which populations of algae or bacteria are around, and dependent on the environment, there's also a change in relation to temperature or greenhouse gases, as mentioned before, as you probably are also aware of CO2 as such. So higher CO2 also changes abundance of organisms, and in many cases, specifically the isotope ratio of those lipid molecules gives us information, for example, how high the CO2 content was in the past.
Yeah. So has it been higher than these days in earlier periods from your data?
Not from my data,
Yeah.
but yes, it has been. So it was in the Cretaceous. Everyone knows a lot of dinosaurs. I talked
Hmm.
about the bone. Yes,
Yeah.
there were also a lot of dinosaurs around because it was pretty warm, and this was the time when there was a lot of CO2 in the air. And usually people are not using the molecular signatures here. They in many cases use, for example, something like calcium carbonate remains,
Hmm.
because they also trap the isotope signature of a high CO2 world.
Okay. So why did you choose this research field?
For me, as a
Yeah.
personally,
Yeah.
simply personally, yes, I choose it because I wanted to become always an analytical chemist. And in my chemical studies, it was rather productive or synthesizing. This was the main focus of the chemist. I'm a chemist.
Hmm.
And so I moved to marine chemistry, and there they had a lot of interesting and fascinating machines, and also they were looking for the environment I'm really much interested in.
Okay. So have you been out doing collecting samples in the field as well, or you're just doing analysis in the lab at home?
Yes, I did analysis also on board, and I'm also took a lot of samples there. For me, I really like to work at home in the lab,
Hmm.
but it's always an exciting experience to be on a research cruise and collecting the samples that at the beginning are just muddy samples. But on the other hand, we are usually on board also analyze the gas components because you cannot really trap gas. It's much easier to analyze samples for gas components right away on board, either coming from the water column or from the sediments. And what is usually the most fantastic experience I had was when we were sampling gas hydrates. It's an ice-like structure, and it was discovered on the ocean floor. So be that it was discovered right at the or on the ocean floor in the late last century, and so we just brought it on board and we lightened it up, the gas hydrate, because there was a lot of methane in it, and it burns, and that's fantastic to hold it in your hands and have it burning.
Wow. Okay.
That's fantastic.
Yeah. Yeah. So what other things do you remember from these cruises? I mean, have you ever encountered a shark attack during those field observations?
Not that I'm aware of. So we usually are followed in many cases by dolphins, many times. So families.
Yeah.
That's that what I saw. But sharks, it's not the right place in the Northeast Pacific. It's too cold. They do not like it. Where I was, or also in the Mediterranean, but maybe in the Caribbean it would have been more risky.
Okay. Or did you see other animals of, notable? So you mentioned the dolphins. Did you see whales?
No, I was not that far up. So what other people always like, if you have sometimes also a research vessel that could dive. So you have an Elvin, which is a diving boat. What's the right expression? It's not a U-boat.
A submarine.
Underwater vehicle, right? And with those people can go down, and that's what many of those really appreciate, because then you see something no one has seen before. Because if you start up the cameras and the light, there are many fascinating creatures in the water, and especially where there's no light.
Yeah. So, right, the topic of our scene or of our story today is about ocean acidification. Can you simply explain what this refers to?
In general, it's an enhancer of an environment to a high CO2 world, especially the water. So there's always physical exchange of the CO2 in the gas phase in the atmosphere with the water, and by this, you get, when you have more CO2 in the air, a higher exchange of that CO2 with the water. It's like when you have at home, you produce your sparkling water from a CO2 smaller gas tank, and then by that, you also dissolve the CO2 in water. You do not really produce sparkling water, but you have much more CO2 in the water, and then you decrease pH. So you simply acidify the ocean.
Oh, okay.
But on the other hand, the ocean is also great because it takes up a lot of CO2 that is getting into the atmosphere by anthropogenic, so by human activity. So there's a buffer associated with the ocean. However, at some point, the buffer is not buffering that much anymore because he's overloaded. So this means you change the pH with time, the more CO2 you bring up into the air.
Yeah. So why should we care then about that? What are some of the scenarios that are being discussed in the scientific realm of what could happen? Or do we, from your all the records, do you see things that happen to the ocean when it's more acid?
Here I simply would refer to what we know from recent times, from nowadays. So you simply know if you add acid to a chalk or carbonate, it dissolves. So you can imagine, so this means a lower pH dissolves carbonates. And if you're, for example, an organism in the ocean, and many organisms are that have carbonate shells, you can imagine that having a lower pH that acidifies or dissolves your carbonate shell, it's hard to imagine that you like that.
Yeah.
So that means, in turn, the habitability of the ocean for organisms producing carbonate shells is getting worse and worse because they have to withstand that lower pH. And the question is how the organisms are changing. And there are reports that they're decreasing in numbers and they're decreasing in size because of that higher CO2, lower pH.
And does that then goes that into the food chain? I mean, would we expect the impact on fisheries, or how is this kind of all linked together?
For sure, there's the trophic chain. This means the less smaller algae that produce carbonate and other organisms we have, the less attractive or the more worse it gets for a higher organism like a fish. And if we get back to the shark, which is at the end of the trophic chain, he will also suffer because there are not much or many fishes available he can eat, he can predate on. And so this means there's always a feedback. If you change an environment, the question how the loop will be. So at the beginning it will be worse, specifically for mankind that use the fish in the ocean.